Hey everybody, today we're going to talk about decomposition reactions. So decomposition, if you think of something decomposing out in the wilderness, it's breaking down. Well, in a decomposition reaction, we are going to break a single compound down into two or more simpler things. So you can see we have this single compound here, and it's breaking into multiple stuff. So how can you identify a decomposition reaction? Well, it always starts with that single compound. Now, much like synthesis, there are many different types of decomposition reactions. So this table that you see here is the same table in a slightly different order as you see on your whole year resources page. So under the chemical reaction prediction rules, down here you will notice decomposition, right? So having that out, having your resources for the whole year is really valuable. And note there's also a special decomposition reaction. It's the spontaneous decomposition of carbonic acid, but we already talked about that in double displacement because we know that even though carbonic acid is aqueous, it makes a gaseous product and a liquid product, which means if carbonic acid is the product in double displacement, the reaction works. But today's focus is not double displacement, it's this decomposition. And much like we did for synthesis, the first thing that I'd like you to do is to go ahead and letter these reactions off. So we are going to say that metal carbonates breaking down is reaction type A, metal hydroxides breaking down is reaction type B, metal chlorates breaking down is C, and binary compounds breaking apart is D. And then if we have an acid that's going to decompose, if it's an oxyacid, meaning it has a polyatomic ion, that's going to be a special case. In fact, so special, I'm giving it a different color. That's going to be case E. And you'll notice we kind of define that as covalent because it's this oxyacid with all nonmetals, whereas all of these have a metal and a nonmetal involved in them. And just like synthesis, the blue ones are a bit more straightforward than the pink ones that have kind of some odd rules that go along with them. So first order of business, let's see if we can identify of our 6 practice problems which letter they represent. So looking at number 1, you'll notice in number 1, it has ClO3. ClO3 we know is chlorate. So that matches up really well with metal chlorate because we have potassium, which is a metal, bonded to ClO3, which is chlorate. So I'm going to put a letter C next to number 1 just so you know which type we're doing. Number 2 is simply a binary compound. Binary, remember 2 things. There's just Hg and O there, so just 2 things. So we have letter D for binary compound. Number 3, CaCO3, well, CO3 is carbonate. So if you look up at letter A is a metal, which is calcium in our case, bonded with carbonate, which is CO3. So this is letter A. And again, I'm just identifying which of these 5 things, which of A through D, all of these different reactions are based on what's there. NaCl is simply a binary compound, only 2 things, so that is type D. And then finally, the last 2, H2SO4 starts with H. Anything that starts with H is an acid. So we said acids are going to be our special type E. And finally, CaOH2 is a metallic hydroxide or a base. Anytime we have hydroxide, that's a base. Bases decompose with special rules, and those are defined in letter B. So let's try this on for size. And let's see if we can use this table, which again will be given to us, right? So this is not something you need to memorize. You're given this, and you'll notice that if you can identify which type of these 5 it is, then we are told what the products will be. So for instance, let's go find letter A, because we are told that if we decompose a metallic carbonate, we're going to make a metallic oxide plus carbon dioxide. So looking at letter A, we know we're going to make a metallic oxide. Which of these 3 things is a metal? Well, it's calcium, right? So the metal is calcium, which is Ca, and we know that Ca is a +2 charge, and oxygen, because we're making a metallic oxide, is O-2. So when we put those things together, we simply need one of each, so our metallic oxide is CaO. And then what's left? Well, what's left over is carbon dioxide, CO2. So how did I know which elements to put there? Again, I'm simply looking at the products that you see up here that tells us as long as I know it's a metal carbonates, doesn't matter what metal carbonate it is, always decompose into a metallic oxide and carbon dioxide. This one turns out that it's already balanced, so one of each of those will get the job done. Let's go to letter B. We are told that a metallic hydroxide is going to make a metallic oxide and water. And as you might notice, a lot of the decomposition things are just the opposite of composition. So if we put together a metallic oxide and water on the reactant side, we make a metallic hydroxide. So it stands to reason that if we decompose a metallic hydroxide, we're going to remake what we started with, a metallic oxide and water. So again, we need to figure out our metal. Well, our metal, the only one there of those three elements that's a metal is calcium. And we are told that we're making a metallic oxide. So calcium's +2, oxygen's -2, CaO gets it done. And then what else do we make? Well, up top in our table, we are told that we make a metallic oxide and water. And we know that water is H2O. Now, in terms of balancing, you'll notice that you have 1 calcium on both sides, you have 2 oxygens on both sides, you have 2 hydrogens, so you are balanced, good to go. Let's go on to type C. Type C is metallic chlorate. Metallic chlorates, how do I know that this one is metallic chlorate? Because it has ClO3, which is the chlorate polyatomic ion. Metallic chlorates decompose into, here it is, metallic chlorides plus oxygen. So what's my metal here? Well, my metal is potassium, right? And potassium is a +1 charge. Chloride is Cl with a -1 charge. So when those come together, you need one of each to cancel the charges, so you just get KCl. And then we're also told that we make oxygen, so we make O. But remember, oxygen is a diatomic, it's one of those Brinkelhoff, so it needs to be O2. And some people might be wondering, well, shouldn't that mean that Cl, right? Cl is also a diatomic. Shouldn't that get a 2? And the answer is no, because Cl already has a partner in potassium, so it doesn't need to go get a friend, another chlorine, to bond with it. This one does need to be balanced. You can certainly make your table if you so desire. I'm going to just simply realize that between 3 oxygens here and 2 oxygens here, the lowest common multiple is 6, so I'll eventually need a coefficient of 2 here, which means this needs to be 2, and we'd need 3 oxygens to finish the job. Going to letter D, binary compounds. These are by far the easiest because a binary compound is made of 2 elements, so all we're going to do with binary compounds is split them apart. The only danger with binary compound splitting is to be aware of those diatomics. Mercury is not a diatomic, but oxygen is part of Brinkelhoff, which is the diatomics, so it needs a 2 next to it, which means we need to balance. We have 2 oxygens on the right, let's get 2 on the left, but that also changes the mercury, so 2, 2, 1 balances for us. We have another type D down here, NaCl. When NaCl decomposes, it splits. We get Na, not diatomic. We get Cl. Cl is diatomic, so it's Cl2. Again, we need to worry about balancing, and again, we're going to get a coefficient of 2, 2, and 1. So that takes care of all of the blue stuff, kind of the more straightforward ionic decomposition. But looking at the pink one, we noticed in synthesis that anytime we have all nonmetals in play, things get a little weird. And so when we have an oxyacid decompose, we make a nonmetallic oxide and water. And remember, when we put together a nonmetallic oxide and water, we made an acid. So we're just basically doing this in reverse. So here are our steps when we decompose an oxyacid. We are first going to write what we know, which is water. Water never changes. Water is always H2O. So when H2SO4 decomposes, we are going to first get water. And then our next step is going to be to balance the hydrogens. But they already are, right? So H2 and H2 are balanced, which means all we have to do now is write what's left. So what's left in terms of a nonmetallic oxide to make this work? Well, there's 1 S on the left, so we're going to put an S on the right. There are 4 S's on the left. We already have 1 on the right, so we need to make 3 more oxygens on the right to balance this thing out. And once we've done that, we're good to go. We have a coefficient of 1 to 1 to 1. Let me show you another example of acids to kind of illustrate this point, one that might be a little bit more strange. What if we had the decomposition of H3PO4, right? So phosphoric acid. If phosphoric acid decomposes, there's something we know right off the bat, which is that we're going to make water, because we know oxyacids decompose into water and non-metallic oxide. So we're going to put in water as one of our products. But this is why I said you need to balance the hydrogens. You'll notice that we have 2 hydrogens on the right and 3 on the left. So the only way to balance those, lowest common multiple wise, is to get them both up to 6. So we need to put a coefficient of 3 here to give us 6 hydrogens, and a coefficient of 2 here to give us 6 hydrogens on the left. And now when we write the nonmetallic oxide, it's a little bit more convoluted. Look what's left over when we write the nonmetallic oxide now. We have 2 phosphoruses. So we have 2 phosphoruses because that coefficient applies to that phosphorus. So we are going to write P2, and this is the only time when you can just magically create subscripts. We normally never just write subscripts, right? We only balance with coefficients, but when we're decomposing oxyacids, we actually just get to write in these subscripts. And what else is left? Well, we have 2 times 4, we have 8 oxygens on the left. However, I've already taken care of 3 of the oxygens on the right, so I only need 5 remaining oxygens from this compound. So P2O5 takes care of this. We balance with a coefficient of 1, and the decomposition is complete. So again, with acids decomposing, again, we've made that a different color because it's a little bit weird. It's a covalent compound. But you can essentially just write down water and then make your nonmetallic oxide based on whatever else is left.